So this is going to be a brief video on a MATLAB program to simulate this device, namely a springy rigid body pendulum, single rigid body, one corner of which is connected to the ceiling by a linear spring. Okay, and we want to simulate this system. We've already looked at how to write the equations of motion, how to describe the system, and so on. So this is just going to be a brief run through of the MATLAB program. Okay, here's the MATLAB program. Usual, we define the mass, we define the spring constant, the rest length of the spring, or the stress-free length. Okay, we can define the moment of inertia parameters to be whatever we want, or we can define them to be specifically based on a cuboid. Doesn't matter, but in any case, these are some moments of inertia, the principal moments of inertia. Here we are defining the integration duration, and here we have all the initial conditions of all the state variables. So we want to track the position as well as the orientation. So this is the position of the center of mass in frame 0 at time 0. This is the velocity of the center of mass in frame 0 at time 0. This is the angular velocity of the center of the rigid body as a whole, represented in the body frame. That's why it's b at time t equal to 0. I've sort of skipped the with respect to 0 here. But in any case, so we've just defined the initial angular velocity to be all 0, just for simplicity. So it's not rotating, it's not translating initially, but it's starting with an initial z, namely the vertical position, that is equal to minus L naught, where L naught is the initial, stress-free length of the spring. Okay. So it's initially starting at z equals that level. And this is the rotation matrix, which we just, for simplicity, pick to be identity. In other words, the object is not initially rotated. It has its standard reference configuration. And then so this is a matrix, 3 by 3 matrix. In any case, so we just assemble all these things into a single long vector: position, velocity, angular velocity, and then this matrix we reshape into a 9 by 1 vector. Something you can do instead of 9 by 1, you can go num-L, which is number of elements of Q naught, comma 1. Of course, Q naught has 9 elements, but if you want to do this for a more general matrix, then you can just use num elements, number of elements, which is going to be 9, comma 1. Okay, so those are the initial conditions, what the state of the system looks initially, and then we just integrate the ODEs and then do an animation, do an even better animation perhaps. Then we can do some checks. Okay, let's briefly look at the ODE file. The ODE file looks like this. Usual stuff. We have time, state variables, some parameters. We unpack the state variables like so: linear position of g, linear velocity of g, angular velocity of the rigid body represented in the body frame. This is the rotation matrix, which is going to be element 10 onwards. 10 to 12 is the first column, 13 to 15 is going to be the second column, 16 to 18 is going to be the third column, and you just essentially take those elements from 10 to 18 and then reshape it into a 3 by 3 matrix to get the rotation matrix. Okay, so that's the rotation matrix that represents the rotation of the rigid body. And then if you want the rotation matrices that do the transformation between coordinate frames from b to 0 or z to 0 to b, It's basically Q or Q transpose. Okay, um, and then we can define the 8 points or vertices on the cuboid. Now, given that, so these are the 8 points or 8 vertices of the cuboid. You can think about what these 8 points mean. And this is in the B frame. So this is relative to the center of mass, right? P1, P2, P3, P4, etc. relative to the center of mass. In other words, it's a position vector from G to P1, G to P2, etc. represented in the B frame. Because it's represented in the B frame, the body fixed frame, these are all constants, right? The cuboid's vertices positions do not change in the body fixed frame. So those are the eight points. Because we only the spring is connected to only one corner of the cuboid, we just keep one of them. I've commented out the other ones, and just assuming that one of them is needs to be calculated. I'm assuming that the spring is connected to the point P1. Not yet, but I'll be assuming that the spring is connected to point P1. That's why I've kept that active. Everything else I've commented out. Okay, this is the vector position of the center of mass with respect to the global origin written in frame 0. That's basically xg dot, yg naught, zg naught. Let's say the spring is connected to point 1, P1, point 1. So I'm writing here the vector, position vector of point P1 from point O, where the other end of the spring, right? The spring goes from O to P1, right? So R O to P1 is R O to G, basically this quantity, plus R G to P1, but R G to P1 we want to write in frame 0, but we know what it is in frame B, so we can take R G to P1 in frame B and then convert it to frame 0 and then add it to R O to G to get R O to P1 in frame 0. Okay. So if you want to write this and comment it out, I would write this as, this is like an intermediate step. Rp1 with respect to O in frame 0 is Rg with respect to O in frame 0 plus Rp1 with respect to G in frame 0. And then Rp with respect to G in frame 0, we are expanding out in this manner. Okay. Okay. Okay, so that we are defining the position, the vector position, the position vector of point P1 in the frame 0 just for future use, because that is a point that is connected to the spring. Okay. Forces on the body, of course, we have gravity, which is just 0, 0 minus mg. And then we also have the spring between P1 and O. Unit vector along PO is this. It's this vector, basically, we just defined, divided by the length, which is the norm of the vector. The spring length itself is just the norm of that vector from O to P1. And then the spring force, this is the vector spring force, is param K, namely the stiffness times the stretch of the spring, and this gives you the scalar component of the force, and then this gives you the unit vector along the spring force. So that's the spring force, this is the gravity force, sum of all forces. In frame 0 is gravity plus spring force. We can also compute the moments on the body about point G. This spring force is in frame 0. We can convert it into frame B here. And we do that because we want to compute the moment of the spring force in frame B, because eventually in the Euler's equations, we are going to write the moments in frame B. So we're going to compute the moments in frame B, for which we need to write the moment arm, or P1 with respect to G in frame B. and then also write the forces in frame B, the spring force in frame B, which is what we did here. We converted from 0 to B, the spring force in frame 0. Okay, so that's the moments due to the spring force about point G in frame B. Okay, so that's the sum of all moments about G in frame B. And then this is the Newton's equations. Acceleration of point G in frame 0 is sum of all forces divided by mass times acceleration. So all this was set up to be able to solve these things. So this is the linear acceleration of point G in frame 0. If you wanted to add some damping, sort of linear viscous damping, we can say some damping coefficient is 0.1. Accelerations equals sum of all forces divided by m, and then an additional force, which basically is c times the velocity of point G divided by m, or something like that. We could do this potentially, and we would have some damping. So here we don't have any damping actually. Damping might just allow the springy pendulum to settle down eventually. That may be interesting to see, but doesn't matter. So I suppose more technically correct would be to actually do the following thing. If you want to add damping, what we should really do is go up here and go sum of all forces equals spring plus gravity plus damping. So that's officially what one should do, but then I'm going to comment it out, okay? Okay, so that's just adding some damping here. Once you've added the damping there, of course, the Newton's equation is still going to be the same, which is sum of all forces divided by mass. That's equal to the acceleration. Okay, and then we had the Euler's equations, exactly the same as before. And then plus you have sum of all moments about point G in frame B, represented in frame B, 1, 2, 3 divided by the corresponding moments of inertia, principal moments of inertia. So that's Euler's equations in the presence of an external moment. That's what that looks like. This is exactly the same as before. These are the rotation equation, differential equation, exactly the same as before. Q dot equals omega matrix times Q, where omega matrix is the skew symmetric matrix written using the omega vector written in frame 0. Okay, and that's it. We then assemble the d state var by dt. In other words, the rate of change of all these variables here. So this is the velocity, which is the rate of change of position. This is the acceleration, which is the rate of change of velocity. This is the omega dots, which is the rate of change of the omegas. And then this is the q dots, which is the rate of change of the q's. Okay, so that's it. That was the ODE file. Now let's run it. So in this root file, we defined all the parameters, the initial conditions, did the ODE integration, and then animations. Let's see what the animation looks like. So that looks plausible, right? That looks plausible. It's falling down, but it's being pulled up by the spring, and it's bouncing around, and it will persist bouncing around forever because there is no damping. So because there is no damping, it will bounce around forever. Now here's a fancier version of the animation. It's got these faces which are transparent rather than just lines. Okay, it seems to slow down just because of some computational issues. Maybe my computer is doing something else. Um, so that's a fancier animation. Let me actually show you what that looks like, what commands we are using there. So the so-called fancy animation is the same as before. It's just using lines and um, simulating those. Here we have the even fancier animation, what I call even fancier animation. You can make the animations more and more fancy, as I'll show. But here, what we are doing is just defining the 8 coordinates of the 8 points in the frame B. These are constants, right? And then the initial position of the 8 points is going to be the initial position of the center of mass, which is this. And then, so initial position of the point 1 is initial position of the center of mass. The initial Q value, the rotation matrix value, if it happens to not be identity. In this case, it is identity, so it doesn't matter. But we can put that in case Q is not identity, times these positions in the body fixed frame, right? So take the position in the body fixed frame, multiply that with the initial rotation matrix, add that to the initial position of the center of mass. That gives you the initial position of point P. And then similarly, you get the positions of all the points. And then there's this command in MATLAB called a patch. Okay, and a patch is essentially a polygon. So what I've defined here is a polygon with point 1, point 2, point 3, point 4. The syntax is you list the x values of all the points in your polygon, y values of all the points, z values of all the points. And then you go patch x values, y values, z values. And then this is the color of the patch. And then these commands tell you how transparent or not that face is. So I'm going to set them all equal to 1. Right, so instead of drawing lines for the vertices, we are drawing faces. This is the face consisting of points 1, 2, 3, 4. This is the face consisting of points 5, 6, 7, 8. Face 1, 2, 6, 5, etc. I'm going to set them all equal to 1 so that they're all not transparent. And then we are drawing a line that connects point P1. Well, it doesn't matter, I guess. P1 initial. Okay, so we've defined the faces, drawn the faces, and then drawn also the line that defining the spring. And then we set that's equal to H1, 2, 3, 4. And this is something called handle graphics. We are using a different technique for animation, different from what we've been using so far in the semester. Just because it turns out patch only works with handle graphics, more or less. You cannot really do hold on, hold off with patch because it doesn't quite work. Okay, so we are setting, in other words, we are assigning this figure or object, the patch, to a variable. So what does that mean? So you can go H1, 2, 3, 4, and it will say patch with properties, blah, blah, blah. In other words, this quantity holds the properties of this object, okay? So alternatively, we can go get H1, 2, 3, 4. It actually has a whole bunch of properties. So in MATLAB, every object that you plot has a whole bunch of properties, and then you can get those properties by using get the value of that plot, the handle of that plot. And we can just look through all these things and try to figure out what they mean by using Google. For instance, edge alpha is the transparency of the edges of your patch, and so on and so forth. So H spring is the line that is used to connect the origin to the point P1. And it's got much fewer properties because it's a line. Because this is a patch, in other words, a polygon, it's got more properties. Okay, and it turns out you can change any property using using the command set. So you can, for instance, set what I'm going to do is increase the line thickness of line width of this thing. H spring, you can go set H spring within quotes line width. And then right now the line width is 1. So look at the line width here. I'm going to press 2 and then press enter, and the line width is going to change to 2. Okay, so the line width just increased to 2. Okay, so you can do that. You can change the line width to 3. It just immediately increased the line width. Okay, so in fact, we are going to use that set command to do the animation. So we're going to say for I equals 1 to how many of our frames we have, the current position of the center of mass, the current rotation matrix, and then we get the current values of all these points by saying current position of the center of mass plus current rotation matrix times the position of the point in frame B to get the current position. And then we just go set the first handle, and then each handle, if you notice, so the handle for the line has the X data, Y data, Z data for the line. Similarly, the handle for the patch contains X data, Y data, Z data for the patch. In other words, the X, Y, Z coordinates that going to define the patch. So what we can do is once we've gotten the new X, Y, Z coordinates, we can just change it instead of replotting the patch. Okay, so that's what we're doing here, set. And then we just do that over and over again, and that's the animation. So let's look at the animation. That's what that looks like. So it looks a little bit different from the animation before. We've made because we've not made the faces officially transparent to the eye, so we can actually change all these things in one go. By doing that, replace all, and I replace all the faces and the edges, their alpha, namely the transparency, to 0.5. So let's see what that looks like. And that's what that looked like. So that you can see the back of all the faces, the back of the cube as well. The line, if you notice, is always visible. It was visible even when things were not transparent, and that seems to just be a property of the line. Okay, that's it. So what we did was do a simulation, MATLAB simulation of the system, the Springy rigid body in 3D. And then also learned about how to do handle graphics using 3D objects. Once you know how to do handle graphics, it turns out that you can adjust a lot of different interesting properties of surfaces. You can change like lighting properties. It turns out there are functions to define camera placement for a 3D animation, the light placement for 3D animation, the properties of the light, the property of the surface, the reflective properties of the surface. You can change anything you want and make a very sophisticated animation. I'll let you guys play with all that if you're so interested. But you can make something that looks pretty photorealistic, essentially using these properties in MATLAB. So let me just stop there.